we've seen that multiple linear regression allows us to look at how variables affect an outcome after controlling for other variables in the model. Just the slope interpretation is, how does a 1 unit change in X affect Y after controlling for the other variables in the model? We saw this great example. How does blood pressure affect your global cognitive performance after adjusting for education, age, and gender? And we saw that it's significant. Look at the other variables that are in this model. Look at age, for example. How does age affect your global cognitive performance? Well, you could probably guess, as your age, the higher age you have, the lower your global cognitive performance. I almost said as your age increases, your global cognitive performance goes down, but that's bordering a little bit on causality. I want to be careful not to say that, even though I know I don't mean that. So I would say people with higher age have poorer cognitive performance. We'll say it that way. For every 1 unit increase in age, I think we could safely make the assumption here that age is measured in years. For every 1 unit increase in age, your cognitive performance goes down 0.02 points. Period. No, comma, after controlling for education, gender, and blood pressure. Now, is that clinically relevant? We see here that it's statistically significant. Well, I don't freaking know. I'm not an expert in global cognitive performance. I don't know how this thing was measured. In order to assess if something is clinically relevant or practically important, you have to ask an expert. You have to ask an expert. Let's look at this other slope here, education. For every 1 unit increase in education, your global cognitive performance goes up, and it's statistically significant. Now, it kind of makes you wonder, what is a 1 unit increase in education? I think it would sort of depend on how these researchers conceptualized and collected that data, right? Could it be for every additional degree that you have, or for every additional year that you've studied? Or could it be comparing people who have education to those who don't as like a binary variable? You don't know. They also have a slope here for gender. This is very interesting. For every 1 unit increase in gender, your global cognitive performance goes up, and it's statistically significant. Now, you probably have a querulous look on your face. What does that mean, a 1 unit increase in gender? These researchers either did something, well, they ended up publishing something that I think it was smart, but I don't know if they did it on purpose or not. Because they're showing here that there is a gender difference in global cognitive performance, that it's statistically significant. Now, the research question is not about gender at all. The research question was about blood pressure, at least that's the title of the paper, and that's the title of the frickin' journal. But they wanted to show us that they controlled for gender, especially because it was statistically significant. But let me ask you this. Who's higher, men or women? We don't know. You don't know. It depends on how these data were coded. It's a binary variable. Let's say they had coded the variable, so men were coded as 1, and women were coded as 0. Now, of course, we know these aren't the only genders, but we can assume that they did this as binary too. We don't know. If men are coded as 1 and women are coded as 0, what is the definition of the slope? What is a 1 unit increase in gender? Well, it means that men are 0.127 units higher than women. But if the data were coded such that women were 1 and men were 0, or even in a way that women were 2 and men were 1, then the women are higher cognitive performance than the men. My hunch is they know the answer. They know how their data are coded. But when they published it, they just wanted to say, look, we controlled for gender. They didn't want to have to get into any sort of argument about who's doing better on global cognitive performance. And this shows us that when we have a binary variable in a multiple linear regression, the coding is important. Let's go back to our babies. Can we predict birth length from gestational age after controlling for a binary variable. We'll use this variable preeclampsia, which is a high blood pressure during pregnancy that can lead to complications. When you have a binary variable and you want to control for it as a confounder, or if you just want to use it as your main predictor, you can put it into the regression model. Just put it in. You say regress, length, gestational age, and the name of your variable. Now, I code my variables in a very intentional sort of way. My variable here is called preeclampsia. And that when I do that, that's the name of the characteristic that I'm coding. And I code it as 0 means you don't have that characteristic. And 1 means you do have that characteristic. This way, anytime I open up my data, if I see a variable and it's called smoker, I know that 1 is smoking and 0 is not. If I see a variable and it's called male, I know that the men are 1 and the women are nothing. If I see a variable and it's called bald, or it's called creepy, or it's called atheist, whatever it is, 1, you have it, 0, you don't. So when I put this in the model, I get a slope. Negative 1.77. And I see a p-value. This condition is a significant predictor of birth length. If you have this condition, your babies are smaller, right? After adjusting for gestational age. Now, I hope you've seen enough that whenever you're looking at predictors of birth length, you sure as hell better adjust for gestational age. It's a very strong, important predictor. So, negative 1.77. If you just take out your notes, it says for a 1 unit increase in X, on the average, babies are 1.77 smaller. But what does that mean, a 1 unit increase in X? Well, I just told you. These are Tibor's data, and Tibor always codes his data so that 1 is yes and 0 is no. If I did it reversed, or if I coded that 1 is yes and 2 is no, what's a 1 unit increase in X? Well, it's going from yes to no. And we would see that that sign would be different. So the variable coding is important. You have to look at the data. Now, when we put both of these in, we see predict Y from X1 and X2. It's a model. We don't need to have all continuous predictors to do a multiple linear regression. We can just take this binary variable and put it in. And we see that we have the same sort of stuff. There's our R squared. Now, I want to make a note that when you add things into a model, your R squared will always go up. You'll always capture some of the variability, even if you put stuff in that isn't important. What colored hair the baby has, what kind of music the mom listens to, any of that sort of stuff, what kind of car she drives. That stuff will all capture some of the variability, and your R squared will always go up a little bit. You see some people use this idea of the adjusted R squared. That's the R squared is a little bit of a penalty for how big your model is. And let's stress again this number, the RMSE, which is also known as the standard error of the estimate. This tells us the standard deviation of prediction. If you come in and you tell the doctor your gestational age, and you tell your doctor whether you have preeclampsia or not, they can make a prediction for you. And they say, I think your baby is going to be this big. And your follow-up question should always be, what's the variability? There's a very famous reading by Stephen Jay Gould. It's called The Median is Not the Message. If you go in and your doctor says, you're going to die, you've got 6 months to live, your next question is, what's the standard deviation, right? You want to know. And that's what this number here does, 2.57. It's a standard deviation, so it talks about individual people spread out around the model. And we know about standard deviations. About 95% of individuals, we said that's most people will be within 2 standard deviations of the middle. In other words, most babies will be within 2 standard deviations, 2 SEEs of the prediction. It's interesting when we have a binary variable because the visualization might tell us a little more, it might inform us a little more of how we can see this sort of stuff. We know how gestational age works, right? As your gestational age increases, what happens to your birth length? It gets bigger. But let's think about this preeclampsia. It's kind of hard to visualize in this 2-dimension. But if you were in this room, if you were in this picture, and you had to walk from, say, here all the way to the other wall, somewhere over here, you'd walk through empty space, and then you would hit like a wall of babies, like one of those beaded curtains, and you'd push the babies aside, and those would be the babies who don't have preeclampsia, the ones who are sitting there at 0. And then you would walk a little bit more through some empty space, and then you would hit another wall or curtain of babies and spread it apart, and you could walk through. And that would be at 0, and that would be at 1. In each of those situations, you see this slope as gestational age increases, birth length increases. Now imagine you could take this picture and you could sort of rotate it so that you were standing somewhere right down here. If you were standing right down here and you were looking right down this line, what would you see? Pause the video and think about that for a second. If your shoulders were squared up with this line and you looked right down this line, what would you see? It's really interesting. What you would actually see is you wouldn't really see gestational age at all because you'd be looking right down it. But you would see a bunch of, hold on, let me erase this. Let me try this again. You would see a bunch of babies lined up here at 0 and a bunch of babies lined up here at 1, right? You would see them. And in fact, you could say, oh, wow, that would be cool. I could put a little box plot on them like this, right? You'd see these 2 lines or walls of babies. Now, what does that picture look like to you? Well, it looks like a t-test. We're going to come back to this and we're going to see that a t-test is a special case of regression where you only have one predictor variable and it's binary. So to recap this, when you have a binary predictor, you can put it in a multiple linear regression to predict a continuous outcome. The interpretation and everything is the same, but the variable coding is important, extremely important. And you'll always want to make sure you know how those levels are coded. You might think next, what do I do if I have a categorical multi-level predictor? Can I put that in the model too? And the answer is no, or well, not yet. We'll do that in the next set of slides.